Good afternoon everybody, welcome back to lecture number 30. متأخرين في المنهج as usual. Here is the summary. April 9, fake quiz 3. April 12, quiz 4. April 14, major 2. We will decide the time. And it's either 6 or 7. بعد المغرب, okay? The final May 13, 8 a.m. Did you get the final schedule? Okay, I'm telling you. Project May 16. Project statement is written May 15, but I'm giving you one more day. Homework 4, we will not have a homework 4. Instead, you either submit the PWM or you submit your CV for revision. If you submit your CV, you have to meet me to get feedback. Otherwise, I'm not going to send feedback, okay? So this is either you submit or not. Deadline for this, you decide, but make it reasonable, okay? Okay?
We send CV, we meet in person or?
Online or in person, if I have office hour, but I prefer online to save your time or my time, okay? Now, maybe we will have somewhere quiz 5 here, okay? And then we might make fake quizzes to contribute to quiz 5 as a replacement. We will decide later. That's one idea, okay? You think about it. Okay? Any other question? Today we will solve examples. Where is your calculator? Calculators. We want to verify the numbers. So we have 35 minutes. Hopefully we'll finish 6 examples, okay? Update. So in the last example, we had a 250 volt shunt DC motor, okay? I told you to redraw the circuit. This is the circuit. This is EA, RA, the field we put it here. Sometimes they put the field on the left. And what is your input voltage? 250, okay? What is your input power? This is not clearly specified, but absorbs 25 kilowatt. This is the whole motor. The whole model absorbs 25 kilowatt. This means it's the input power. Okay? Now, we calculate IF. What is IF? 250 over RF. What is RF? 125. So it's usually small current to amp. So I line, you get the I line from where? You get I line from the problem statement. It's a 12. Sometimes you get it from the power factor, loading, etc. If it's AC, but this is DC. Or sometimes you get it from the input power and the input voltage, which is 25 kilowatt over 250. How much is that? Medium. Medium. 100 amps. So, this is at no load. This is at no load. Full load current is 100, okay? Now, so I line, or sometimes we call it I terminal, is in the statement 12 amps. So from these two, what is the armature current? 10. Okay? Then he calculated EA. How to calculate EA? is Vt minus Ia Ra. And if you do the math, you should get 247.5. Okay? So this is a smaller, so we have 3 volts drop across the Ra, armature resistance. Okay? Keep in mind here that omega is given as 1000 RPM. So omega is what? 2 pi over 60 times 1000. This is in radians per second, which is what? 104.72. So if you usually we try to connect omega and Ea to calculate what? The constant. Okay? The motor constant is not given. To calculate فراس شغالة الكاميرا؟ Okay. So we have the formula EA equal K. Here we have KA times IF. Go back to the formulas. There is multiple formulas. Okay. The first formula we started with is this formula, which is Ka times the flux times omega. So Ka times theta is a constant. This is the same one as in the project. The other way is if you say the flux is K times If, it is KFIF. This is the other one as a function of the field current. So you have the field current. However, you can redefine it more using the torque equation and have a constant called Km, which is Ea over omega, where Km is KFIF, which is equal to KFIF equals to this Ka times the flux. Clear? So keep track of what we mean by the notation. So here in this example, we are trying to calculate Ka times If because he is telling you, because the field current is constant. The field current is constant. Okay? So Ka times If is the constant. K times omega, I think it was called K, big capital K. So K equals to Ka times If, which is equal to Ea 247.5 over 104.72. What is this constant? This is 2.36. What's the unit? Volts over radians times second. Okay? This is one constant, K. The other constant is Ka, which is K over If, which is the one shown here, 1.187. Okay? So let me write the correct notation. What is the right term for this capital K? Call it Km. This is Km. Okay? The motor constant overall with the field. If you divide by the field, this is Ka, armature. Clear? If you provide this or this in the test, it's fine. However, I am more leaning toward this constant because this is the same one we're going to use in the project. This is the same one. This is Km, which is equal to K times the flux. Clear? واضحة? So this is the one that the motor constant with the field. Without the field is a smaller number. Both are correct. What's the unit of this? Voltage second over radians times amp. واضح? Please don't confuse yourself. Now we found the constant. After finding the constant, what will happen? We have to find so calculate the motor constant. So to me, the motor constant is this, not that. That's why I put it in the board. The last statement, any question? Please ask. These questions will come in the test, okay? You have maybe 6 or 7 examples. I'll bring 1 or 2 in the test. Calculate the speed regulation torque at full load condition. Now we did A and B at no load. صح ولا لا? Because we have the no load current is 12 amp. Full load, the story is different. At full load, we already know that we calculate the rated current. We already did it before, which is what? 100 amp. So part C is at full load. Okay? Yes. Yeah. At full load, what do we have? At the full load, we have I terminal is 25,000 over 250 is 100 amp. So the terminal current, when we connect the load, increase from 12 to 100. Now we can get the field IF to be the same 2 amps. The field will not change. Why? Because the same 250 is applied on the RF. The field current IF is the same. Even if you connect the load, the only one that will increase IA, it will be 98. So this implies the full load armature current IA is 98 amp. So now get the new EA, which is VT minus IARA. You do the math, this is 225.5 volts, so it dropped a little bit. EA dropped a little bit. So what does he want? The speed regulation at torque at full load condition. So what is the motor speed? Now we calculated the motor constant. We already know that the motor constant. Now we calculate, we use the formula. EA equal Km times omega. We have EA, we have Km. What is omega? 225.5 divided by my constant, not the slide constant, 2.36. The project constant, the motor constant. If you do the math, you should get the same answer to be 94.98 radians per second. Sometimes they calculate it as N, so this is full load, this is omega full load. What is it is 60 over 2 pi times 94.98, and you get the RPMs, which is usually smaller, which is 907 RPM. Okay? I don't care about the zero. Yes?
هي دائم 2.
وش دائم 2؟
1.87 ضربها ب 2.
لأن الفيلد كارنت، بس أنا سميته هذا KM.
مسكت الفلكس يعني دائما حاط يحطها 2.
لا, it's written in the statement. The field is 2. Yes. Okay, but the field is usually constant, no matter what. If it's shunt. في الشنط هل في IF في السيريس؟ ما في. في الشنط was series separately excited, the field usually assumed to be constant. But in this course for 6.2 we will have examples where we change the field. What will happen if we change the field? Speed will change. In 360 we did not change, so this is 360 still. So to get the speed regulation is easy, 1000 minus 907 over 907, you get 10%. And the torque, how to get the torque? Use any of the equations, but this equation, what is EA over omega M? Is Km, صح? Km, we already calculated it here. 225 over 94 is Km. Times the IA. This is one of the equations. If you do the equation 98 times 2 point something, you should get the torque to be 232 Newton per meter. And finish problem 1. Okay? let's do problem 2, where we talk about the control. A DC motor, so any question about example 1? Study it, okay? Study it. The example number 2, I want to remind you one more time that this example is optional, okay? This is for your knowledge, not required. Why? Because we are doing a similar one using the project. You don't need to solve these equations. Let's do example number 2. DC motor develops a torque of 30 Newton meter. Is this the load torque or the output torque?
Output torque.
That is the output torque. There is no information about the loading conditions, correct? So here, what is the equation here? Ka times theta. Ka times theta is Km, the motor constant. It's the same story. Find the torque when the armature current Ia increased by 50, flux decreased by 10%. So initially, what do we have? Initially, we have T1 equal, this is another problem. What's the equation? Ka flux M Ia1, and we have torque 2 is Ka flux M Ia2. We already know T1. We can write T2 parameters as a change. So this is Ka. The flux is decreased by 10%, so this will be 0.9. This is 1. This is 2. Ia will increase by 50, so this will be 1.5 Ia1. So I know T1 is 30, T2 is unknown. I can divide this, get rid of the similar ones, and find the answer. So you'll have T2 over T1 equal Ka times 0.9 flux 1 and 1.5 Ia1 over Ka times flux 1 times Ia1. Cancel, 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 cancel. This is what? 30. So T2 is what? 30 times 1.5 times 0.9, which is what? 40.5 Newton. Clear? For the same machine, if you increase the armature current, it will increase the torque. If you decrease the flux, it will decrease the torque. Because the equation here is clear. They have the same motor, and there is a relationship between theta M1 and theta M2 and Ia2 and Ia1. Is this example clear? في سؤال عليه? Let's go to example number 3. So is this 360 or 462? No, this is 460. Not 360. Example 1 is 360. Because if you change the flux, it means you change the field.
Oh, like flux constant.
Yes. Another shunt motor example. A 250 volt DC shunt has an armature resistance of 0.1, field 250. At full load, input power is 14 kilowatts, 250. Speed is 1000 RPM. Calculate the speed regulation. Neglect armature reaction. Okay? Neglect armature reaction. It has many meanings, but one of the meanings is ignore rotational losses. Okay? So how to solve this example? First, you have to find, do we have information at no load? Do we have information at no load? Read the question. كله يتكلم عن الفول لود صح ولا لا؟ it means I don't have I no load, I full load. I jump directly to full load. So what is at full load? What do I have? I line is power over voltage, which is what? 14 kilowatts, it's written in the problem, over 250, which is equal to 56 amps. Then what do I have? The field. How much the field? 250 over RF, which is what? 250. So from these two, what is the armature current at full load? This is at full load. 55. So what is EA? VT minus RAIA. You do the math. 2244.5. From the equation, I can get the Km, which is EA over omega. This omega is full load. It is the same as omega M. You need to learn different notations. This is from another textbook. But you need to know what are the subscript meanings. So here, for example, here they're using another rotation, V over RPM. Did he convert it? Here, I'm going to tell you what he's doing. But I'm going to solve it my method, and you're going to see this method, and you're going to understand. What is the constant Km? 244.5 over omega M. What is omega M? 2 pi over 60 times 1,000. I want answer, please. Calculators. Nawaf, where is your calculator?
I forgot.
244.5 over 2 pi times 1,000.
2.3
كم constant?
2.3
2.335. Okay? What's the unit? Volts over radians per second. So what is the omega at no load? At no load, if I ignore armature reaction, it means at no load I ignore RAIA, no rotational losses. So here, because neglect armature reaction, IA no load equal to 0. Focus with me. This is the definition of neglect armature reaction. There is no IARA at no load. There is no rotational losses. So this implies EA equal to 250 volts. So this implies omega no load is EA over Km, which is what? 250 over the 2.334. Which is 107.11 radians per second. So what is the speed regulation? 110. What is omega full load? I forgot to get the number. 2 pi over 60 F. 104.72 radians per second. So it is 107.11 minus 104.72 divided by, is it full load? Divide by 104. So how much I got? 2.29%. So this is if we're gonna solve it using our formulas. In the slide, how did he solve it?
Using the
He got the constant as a function of V over RPM directly, without changing to omega. Get it? This side, get it? Did you get it? In the slide, he got the constant K times the flux as V over RPM. The way I did it, our own method, is get the constant as V over radians per second. But what is the cost? I had to convert the 1000 to RPM. Here he didn't get it, and he got the final answer in RPM. Yes?
because he is asking for the speed regulation, which is
Yes.
unitless.
But
So
yeah,
it's-
unitless. It doesn't matter if you do omegas. But the key here is we have two different constants. One constant as a function of voltage over RPM, and the constant I did the same we do in the class as a function of V over radians per second. Get it? Get it? So you have to watch YouTube now. Those who missed the class and didn't watch the YouTube, when they're gonna look at this slide, you see how did he get that? And they're gonna waste 25 minutes trying to understand it. Okay? Okay? في سؤال على السؤال هذا؟ Can we jump?
Yes.
Let's jump. Example 4. Is it still recording? Firas.
Yes.
Yes.
Here we're going to have more control. A 220 volt, 7 horsepower series motor is mechanically coupled to a fan and draws 25 amps, runs at 300 RPM when connected to 220 supply. There is no external resistance connected, so the only series resistance is RA and RF. The only series resistances are what? RA and RF. The torque required is proportional to the square of the speed because it's a fan. RA is 0.6, RSR 0.4. What is R series? The third one? 0. Neglect armature reaction and rotational losses. Find the power delivered to the fan and the torque developed by the machine. Before we go, let's review quickly a series. Even though I do not like the series motor, but it's required in this course. So do you remember how many resistances we have? We have RA, we have RAE, we have R series. So this one is variable. This one acts like RF, but we don't have a field because it's on the series. And here we have the, why do we have the windings in? For transient, for simulink. Okay? So what will happen in the DC machine, in the series? These are the equations. EA is VT minus IA times the summation of whatever R's we have. And the torque is proportional to the gain times square. So we really need to find this KSR using the torque. And then we're going to design our problem, omega, by adjusting RSR, which is this resistance. We're going to add it to reduce the speed, because if you add R, what will happen to the speed? It will decrease. So this example shows you how to control the speed in a series DC motor. Let's see the example. So the first part, find the power delivered to the fan and the torque required. Did he give you IA? Yes, it's 25. So what's the formula? EA is VT minus IA times, I forgot the notations, RA plus R SR, oh my bad. So it's actually RSR is the one with the arrow. No, RAE, the one with the arrow. This is the one with the arrow. هذه الR هي اللي فيها arrow. So this is the variable. RSR is already fixed. This is 220 minus 25 times 0.6 times plus 0.4 is what one? What is this answer? 95 volts. 195. Clear? Let's continue. What is the power? Because the question is, find the power delivered to the fan. Where is the fan is connected? To EA directly. So the power that goes to EAIA is the same power as the fan. So the power is what? EAIA. Yeah, don't say VT times IA. This is the input power. This is the output power. This is the one that goes to the fan after losing the voltage drops across RA and RSR. 195 times 25. How much? 4.88 kilowatts. He's getting it in horsepower. Just to show you, it's 6.54 below the 7 horsepower. So is it full load? No, it's not full load because full load is 7 horsepower. So this fan is not full load. Very close to full load. And then what else we have? You get the torque. Torque is what? Power over omega, which is 4.88 kilowatt. What's omega? 300 RPM. 2 pi over 60 times 300. If you do the math, how much the torque? 155.2 Newton meter. So we finished it. The torque and the power. Then, the speed is to be reduced from 300 to 200 RPM. What should we do? For the series motor? Add series resistance. The more resistance we add, go back to the series. Add a series, okay? This is the series motor slide. This is these two are fixed. You can increase this RAE. If you increase RAE, what will happen to the speed? Decrease. However, your torque is constant or not. What is your torque? Is it constant? No, it's a fan. It's a fan. You agree with me? So because it's a fan, it's K omega squared. So we have to go across the trajectory. So if we are at 300 to 200 RPM, we have to go from this point to this point. Get it? This is a fan. K omega squared. That's a project. So if we increase the resistance, we have to jump from this point to this point to this point to this point only. This is the operating point, which is the intersection between your load and your machine. Clear? So we need to calculate KSR. We have the torque, we have IA squared, we need KSR. Why? Because KSR we can use it for the omega equation. We know VT, we know IA, we just change the resistance. Let's see how he did it in example 4 or 3. I forgot what example it is. It's example 4. So using this equation, he got KSR to be 155.2 divided by 25 squared. Torque equal KSR times IA squared. We know the torque, we know I squared, so KSR is what? 155.2 divided by 25 squared, you're gonna get 0.248. This is another constant. You have to put it in the formula sheet. So, what will happen if you reduce the speed? What will happen to the torque?
It should decrease.
It should. What is the formula? Torque is a constant of the load. We don't know what is this constant, times omega squared. صح ولا لا؟ هذه الفان. You agree with me? We don't know what is this fan constant. I'm going to call it K of the fan. So at omega, if I reduce omega, what will happen to the torque? It will decrease. If it was a constant load, it will stay constant. Because it's a fan, it's a little bit more challenging. So how to do it is you have to get you just do 200 over 300 squared times the original torque. You're going to get it as 68.98. The proper way is you have these two divided by T fan. This is 1, 2. They have the same constant, omega 1, omega 2. Solve it. If you solve it, you're going to get this equation. Because the constant of the fan will cancel. That's the professional way. Okay? That's what? The professional way. This is what? The shortcut way. So in this course, understand, it's T omega 2 is omega 2 over omega 1 times T1. You can write it as a formula. But a smart student will understand if we decrease the speed, you're going to decrease the torque. I said in the video, if you increase the speed, decrease the torque, that's wrong. If you decrease the speed, you decrease it with the fan. And then what will happen? You're going to have a new IA because you have
Different torque.
new torque, different torque. So what is IA2, the new IA? You're going to use T2 over KSR, which is what? 68.98 divided by 0.248. You're going to get it's 16.68 RPM. We will continue next lecture this example. Okay? So let's stop the recording.